So can you see my screen? Yes, no, please.
Yes,
Yes.
sir.
Okay. Okay, so let's get started. So we started with sliding window flow control, and just to recapitulate quickly. So we saw stop and wait is very inefficient because it waits too long after sending one frame. So sliding window was you allocate a buffer space for W frames on both sides. And the idea is that if it is W frames, then the sender can send W frames without receiving an acknowledgement. So at any point of time, there can be W number unacknowledged frames on the line that the sender doesn't want the acknowledgement. Maybe the receiver has received it and sent the acknowledgement. It has not received by the sender yet and so on. But the sender can send at most W frames, not one frame, without receiving an acknowledgement. And this is what is called a sender window. Similarly, the receiver can also have a window which says which are the frames that I can receive. And we'll just look at an example. And so what we do is basically we put a sequence number with each frame. I'll come back to this slide. Each frame has a sequence number. So remember, we put different things on the thing. We put the frame check sequence. We put a preamble, okay, which is not really counted part of the frame or something. So now I'm kind of adding so this business about the header of a frame. We'll see. So you will slowly start seeing things that will, occur throughout the course. Okay, so anytime we need to send some control fields, which we call a header. And one of the control fields I'm sending is the sequence number. And so any number of bits that I reserve is bounded. So if there's a k-bit sequence number, then your frames can be numbered from 0 to 2 to the power k minus 1. Okay, and then it will wrap around again 0 to 2 to the power k minus 1 and so on. And these are the two things that I want to recapitulate, because this is something that is omnipresent in higher layer networks also. We'll see that when I acknowledge a frame, I do not say if I received frame 3, I do not say I've received frame 3. Okay. In networks, you will say I expect frame 4. So that automatically means that you have received everything up to 3. Not just 3, but up to 3. That is the advantage of this basically. Okay. So I will always send the sequence number of the next frame expected, which means if I say ACK K, let's not use word K, ACK X, this will imply received everything till x minus 1 properly. Okay. And also it can be used to acknowledge multiple frames. This is actually what I just mentioned. So typically just to reduce the number of frames that I need to send, because with every ACK frame also we'll see you have to put some headers and so on. We'll see later. Okay. So you can actually, this is what we call cumulative ACKs. So I receive 1, 2, 3. I don't send any ACK. I just wait. Maybe another 4 is coming. Maybe another 5 will come very fast. Okay. But usually there is a maximum time window. So I get everything that I get in that time. And then I say what is the highest ACK that I can send. So I send a single ACK 4. I don't send an ACK 2 or ACK 3 or anything. But then if I get 1, 2, 3, 1, 2, and nothing comes for quite some time, I'll still send an ACK 3. Okay. So idea is just this very simple common sense idea. Rather than sending an ACK frame for every frame that I receive, which is inefficient. Okay, because every ACK frame will also, I'll need to create it, put some header, transmit it, and so on. I wait for a small amount of time. I see all frames that I receive within that time. And then I send a cumulative ACK for all of them if all of them are in order and so on. Okay. To indicate this, as I said, an ACK X will mean I have received all frames till x minus 1 correctly. That means all the frame check sequence, everything matched. Okay, with this, look at this picture. Let's spend some time on this picture. You will understand sliding window. So This is the window, this blue thing that is going to slide. Let's go through. This is the sender side. Forget about the bottom part. Okay. So these are my frame sequence numbers. I'll say 0, 1, 2, 3, 4, 5, 6, 7 again 0, 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 3 and so on. So here my window size I have taken to be 7. Okay, this is a 3-bit window. Okay, all right. So this is the last frame. Just suppose at a situation, this is send 0, 1, 2, 3, 4, 5, and 5 is the last frame that is acknowledged. Okay, but the sender has sent. So when the last frame 5 was acknowledged, okay, that means you can send another 7 frames without receiving acknowledgement. That means 6, 7, 0, 1, 2, 3, 4. And let's suppose it has sent 6 and 7. So this is the last frame transmitted. But it has not received any acknowledgement for them so far. So the maximum number of unacknowledged frames that the sender can put on the line is 7. So this too it has already put on the line. So it can now put 0, 1, 2, 3, 4 on the line, but no more. Until it receives another ACK, which will do something. Okay. Now what happens if it sends 0? Sends 0 also, then that will be one more frame that it has sent for which acknowledgement has not received. So this window will move here. Then it sends 1, this window will move here. Okay. So these are the frames that you can have not sent yet. This is the window. You have not sent yet, but you can send without waiting for anything from the receiver. Okay. Now think, so this is the trailing edge of the window will move as I send the frame. So trailing edge strings. Okay. Now suppose you receive the ACK for 7. That means you receive an ACK 8. Okay. So this tells the thing that, and let's say just again go back that you have not sent anything yet, just suppose. So this basically says that everything up to this frame 7 has been received by the receiver, which means now the number of unacknowledged frames can be 2 more out here. So this window will now move here. So window will expand as you receive the ACKs, this window will move forward. As you send things, the window will move for string from this side. And if you look at this window at any point of time, these are the frames the sender is allowed to send right now without waiting for anything. This is why it's called a sliding window. The window slides. Okay. As you send, the windows, the back last part of the thing shrinks. As you receive ACKs, this increases. These are not the ones that are sent. These are the ones you can send without waiting for anything from the receiver. Is this clear? Yes, no?
Yes, sir.
Okay. Now, what happens on the receiver side? Receiver also has similar window. Okay. So if this can send W, I can also receive W unacknowledged, or with before I send an acknowledgement. Okay. So let's say this 5 is the last frame acknowledged because that is what it has sent. Now suppose this 6, 7 that the sender has sent, it has received, but it has not sent an acknowledgement so far. Okay. Which means basically the other frames that it can receive, it knows the sender can only send me 0, 1, 2, 3, 4 before I send the acknowledgement. Okay. Which means that my window will be this. These are the other frames that you are expect. You can accept if they come. If anything else comes that somehow there is an error somewhere, so you will not accept it. Okay. Now, as the frames are received, the window will shrink from this side because this is already received, not something that may be received, may be accepted. Okay. As you send ACKs, the window goes on this side. So basically, as you send ACKs, you know that I have already sent the ACKs. Maybe the receiver sender has received it. Therefore, the receiver will send me another W size window. Therefore, I should expect that many frames. So again, the receiver's window shrinks. Anything else that I get outside of this window, for whatever reason, is an error. Because the sender can send me only this once. Because I have received already 6 and 7. I have not sent the ACK to window the sender for 6 and 7. Okay, which means the sender can only send me 6, 7, 0, 1, 2, 3, 4. I've already received 6, 7. These are the ones I should expect. So the window kind of slides on both sides. Is it clear?
Yes, sir.
Okay. Anyone has any questions? I'll wait for 10-15 seconds. The sliding window is going to be very, very important. Okay. Later on, we'll see TCP at the TCP layer also. Okay. And right now, we have assumed we'll just do it in like 10 minutes time.
Yes,
Right
sir.
now,
So I have
yeah, go ahead.
one confusion. So, sir, we have acknowledged the frame 5,
Right.
and still we can receive 0 to 4.
Yes. But there's, see, that is fine, because see, this is a continuous bit stream.
Yeah.
I have got a continuous bit stream. I have just broken it up into frames and numbered these frames. Okay. But I have only 3 bits for the frames in the header.
Okay.
Okay. So after I have numbered these two up to 0, 2, 3, 4, 5, okay, 6, 7, what will be the next frame numbers? We'll have to wrap around.
Yeah, that will be 0.
Then 0, 1, 2, 3, 4, 5, 6, 7 again. Again 0, 1, 2, 3, 4, 5, 6, 7. But this 0 and this 0 are separate frames. They're 2 different frames.
Yeah. Okay.
This is the continuous bit stream that I'm transmitting. I want to transmit a file. Okay, my frame size is only, let's say, 500 bytes. I want to transmit a file that is 1 megabyte. I just break it up into 500 byte chunks, put that control fields, compute the FCS, frame check sequence, put it at the end, and then send each of them with a preamble and post.
Okay.
Okay. Now, but you have hit on something. This is why, okay, we have, what can this window size be? It is related with this k bit sequence that I have. So window size, okay, cannot be more than 2 to the power k minus 1. I will do one for the error control shortly. You will get an idea. There also we'll see, along with this, I will say that what if the ACK gets lost, what if the data gets lost, and so on. And I will, again, you will see the sliding window plus something there. Okay, I'll do that computation there, but you need to also see, even without errors, why is the size limited to this? But let me do that, you will get an idea. But the idea is, if you use k-bit sequence numbers, that means your frames are numbered from 0 to 2 to the power k minus 1. This W here cannot be, so W must be less than equal to 2 to the power k minus 1. The size of this thing cannot be, so there's a trade-off. It's not that you can send 1000 frames. The core idea is very simple, because then when an ACK comes back, you will not be able to distinguish which zeros ACK it is, which one's ACK it is, and so on. But it's slightly more complicated than that. But these are again the things that we don't do in class or something are good exam questions. You can easily say, show a counter example that with k equal to 3, your window size cannot be 8. So then you have to tell me basically that this is a sequence of operations that will cause some problem. But I will do at least for one of the cases later on, and then you should try it yourself. That you understand it very well. And if you want to do it the easy way, it's done in like 100 different places in the internet anyway. Okay, but you understood basic sliding window flow control, right? Okay. Okay. So with this, now there is some small things. So the actual window size, when I said k and I said the maximum is 2 to the power k minus 1, it is maximum only. Okay, you can do anything smaller also. Okay? Because see, that much buffer you have to keep. Sometimes k may be large, but then you don't have that many buffers. Okay. So even with k equal to 3, you can say, no, I don't want 7, I want only 5. So these are more optimizations. And the other side is, right now we have, this is another technique that you will see a lot. Okay. I have only said this, what if A wants to send frames to B? Okay, but usually communication is both ways. Other than the acknowledgement also, even for data, we may want to send some data frames to A. Okay. And then now with each frame there is some header information which is over it. This control fields that we have talked about. Okay, we'll see it again and again and again as we go on. Okay. So rather than sending the ACK for this frame separately, okay, I can put the ACK for this frame in a data field out here if I design the thing suitably. We'll see it when we do TCP. Okay. So this is what is called piggybacking. It's kind of you are piggybacking, riding over the original data frame on the direction to kind of the ACK frame is riding over the data frame. I kind of club them together so you don't have to spend the overhead of putting the control fields on both the frames, basically transmitting both the frames and so on. Okay. But again, there are trade-offs. We'll see. So each data frame will include a field that holds the sequence number of that frame, plus a field that holds the sequence number used for that. And if a station has an ACK but no data to send, it will send a separate ACK frame in. But if you have a data frame, you save the cost of an ACK frame. This is just an optimization. Standard term is piggybacking. We'll see it a lot, so I thought I will introduce it here. So both these things are kind of optimizations. It depends on how much buffer you have. Okay, trying to reduce number of frames, but the basic technique remains the same. Okay. So last part of the puzzle is, so far we have seen error detection and so on. Okay, we have seen how to do flow control and so on. But then if I detect an error, what do I do? Remember, our goal was to make reliable communication between two parties. That means everything that the first party says should be received by the other one eventually correctly. I cannot say the first time it will be received correctly. As you have seen, there can be different errors, noise, etc., etc. But then I want to ensure that eventually it is received correctly. So error control deals with this. It ensures the finally received bit pattern is same as sent bit pattern. But as I said, may require more than one transmission. I cannot guarantee one transmission. So what are the types of frames lost that you can see? Damaged frames we saw. Okay, some bits got corrupted. The 0 became a 1 became a 0, and so on. Okay? And we have seen that there is a frame check sequence, and even though it's not 100%, we can detect a lot of errors. So this is the error detection that we do. What is a lost frame? We'll see this term. How can a frame be lost completely? I can understand it gets corrupted and comes back damaged, I detect it. Or if I don't detect it, I have got a frame. I just has an error, but I could not detect it. But in both cases, I have a frame. So how is it possible that a frame can get lost? Anyone? Any clue? That the sender sends a frame and the receiver does not even get it. Remember, 1 becoming a 0 is not getting a frame. It's still getting a frame with a 0 bit value. So any clues? How can a frame get lost? So this is slowly where I want you to kind of, put a picture in your mind. This is where the Blackboard really helps, because at the beginning of the class you draw some pictures, it stays with you for the entire class, not like shuffling through slides here and so on. Okay, but we don't have that, so I request you to try. Always remember, when you talk about frame, the frame structure. What did you had? You had control fields, you had data, and then you had control fields again. Okay, this is FCS and every frame check sequence and everything is part of the check bits are part of this. Anything else you had in the frame when you transmit a frame? Yes, no? So this control field, for example, we just saw one field into it, the sequence number, for example. Okay, so this is the sequence number. Okay, for example, here it is the check bits. Okay, for FCS. Anything else you had in the frame? Come on. When you transmitted a frame, did you transmit anything else? How did you detect the start of a frame? Anyway, when did a frame start? The receiver is waiting. How does it know the frame has started? Some frame is going to come. Anyone? Can you hear me? First of all, yes, no.
Yes, sir.
You had the preamble and the postamble. Remember?
Yes, sir.
So get these things, you need to start studying and kind of thinking a bit and putting things together in your mind. It's not easy, okay, but practice, okay. So when just try to visualize what happens the sender wants to send. It sends a preamble, it sends the frame, it sends a postamble. Why does it send this? The receiver is waiting. It does not know when a frame is going to start. It's just sensing the line. It needs to know that this is now a frame is starting, because just a spurious signal on the line is not a frame start. That's why you put the specific preamble pattern. And then you send the data and everything. It needs to know when the frame is over, if there's a variable size frame. That's why you put the specific postamble pattern. Okay. So a lost frame is, for example, a preamble got corrupted. So you kept on seeing data, you kept on seeing zeros and ones, but you did not get the preamble bit. Okay, the pattern, exact pattern for the preamble. And therefore you think that there is no frame. It was just Fourier signals happening in the line. I did not get the preamble, therefore I would not take it as a frame. Are you with me? This semester is going to be tough. Let me tell you, sixth semester is always the killer semester. Okay. So you need to plan your time. You need to not have things pile up. It is an online semester. Actually, I'm taking a sixth semester online for the first time. Okay. And I don't like it. But I am sure you don't like it more than me. So if you have feedbacks to give me, send me feedbacks. So this is what is happening. This is how the class should go. This is what we are finding difficult and so on. But don't let things pile up. Then you will not hit with all the lab starting and everything. You will not know what hit you, basically. As part of that, slowly, as I said at the first class, I would like you to kind of not just go through lots of slides. Other section will have lots of slides. You can mark. I can give you references. But try forming a picture of what is happening. It will help you understand the network better. Anyway, so I can have lost frames or damaged frames. And error control deals with two things. This is what that error recovery, is called forward error control. So this is basically the one that I talked a little bit, saying that it will require you to error correcting bits and so on. So you don't go back, you just get something and you correct it and move on. Okay. So this is something we will not do, because this is not usually what is done in the protocols that we'll study. So we'll do what is called backward error control or error recovery by retransmission. Okay. And this technique is called automatic repeat request. So ARQ is a word that you will see a lot. What is ARQ? First thing, same as earlier, break up the bit pattern into fixed length frames. Okay, remember, the data that you want to send is a long chain of bit pattern. Framing is something that you are doing, break it up in order to send through the networks, because I want to do all these other things, flow control, error control, etc. Okay. So I break this into fixed length frames. I add error detection bits. I know how to do it. And then the receiver will check it on the other side to detect errors. And basically, it's very simple technique. Ask the transmitter to retransmit the frame that show error or that are expected but not received within a timeout. Okay. So for example, if I have 1, 2, okay, and so I'm expecting 3. Okay, I don't get 3 within some time, but I get a 4. Then I know there is something missing. These are my frame sequence numbers now I'm talking about. Okay, and then I will ask the transmitter to resend 3 or something else, as we see, depending on the technique. And then, so you wanted to send a bit pattern, you broke it up into frames, do error control on individual frames, and then put together all the frames to get back a bit pattern. So have this picture in your mind. You want to send a large file, which is just a 0-1 pattern. We're no longer talking about lower level signals and all these things. Okay, I have a digital file, which is a large file, but then I will not send large file together. I will break it up into frames. Each frame I will put some control fields, preamble, postamble, send it on its way. The other side is going to get each frame, do error detection on it, do error control on it, flow control on it, and so on. And then when eventually everything is ready, it has got all the frames in order, is going to give me the entire thing together. That's sort of the idea. Okay. The first one is stop and wait ARQ. The same as earlier, okay, as the sliding window sort of, but now there is error involved. So sender, I'll just transmit one frame. Only when I hear the other side has received it properly, then only will I transmit the next frame. So same as stop and wait, only thing is that because now frames can get lost, because my data frame did not go or the ACK frame did not come back, the sender may have to retransmit the frame again and again. Okay. So there are two possibilities of error. Either it does not receive the frame or receive a damaged frame. So receiver will simply discard a damaged frame, not do anything. Sender will time out, reset the frame. So receiver will not, in the simple stop and wait ARQ, will not send anything saying this frame is damaged or something. It doesn't happen because this frame is damaged, is that information can anyway also get lost. Basically, that acknowledgement frame can also get lost. So only when the receiver gets the frame properly, it will send an ACK. But then that ACK may also get lost. So the only time one frame is complete is when the sender has sent it and the sender has received the ACK for it back from the receiver. Then I say this frame is complete, send the next frame. So I do one frame at a time. Okay. And then all these other possibilities, you receive the frame, but the ACK is lost or damaged, sender times out, discards the ACK, sends the frame again. But now you see the receiver can receive the frame more than once. Because I may have this situation, this is my sender, this is my receiver. Sender sends, this gets lost or damaged. So sender times out, thinks that the receiver has not received it, sends again. So this now is duplicate. Okay. So then how do I know? Remember in the plain stop and wait ARQ in the sliding window, when we did not talk about errors, I did not need anything else. Okay. So what I do now is basically, I also add a 1-bit frame number because only one frame can be in transit, unacknowledged at any point of time. I just need 1 bit. Okay. So I add a 0 or a 1. And the ACK will include the frame number. Same as earlier, ACK 0 means it has received frame 1 and is expecting the next frame to be 0 because these are the only two possible numbers. ACK 1 says it has received 0 and expects 1. Okay. So this is how I handle duplicate frames. It's a very simple example. I think you can read yourself also. So it's a proper no error case. Frame 0, ACK 1. Frame 1, ACK 0. No error case. Now frame 0 comes here, gets lost. Receiver does not even know frame 0 is coming. You don't know when the other side is necessarily going to send always. Okay. So, but then the sender does not receive the ACK. So sender will time out, send frame 0 again, and the ACK 1 will now receive it. The other case, it sends the frame 1 now. Okay. Sends the acknowledgement gets lost. So frame 1 sends again because receiver sender times out. Okay. And that comes. The receiver never times out in this case. The sender is the one that times out. Pro is simple, only one bit. Con is extremely inefficient, as you have already seen. So even if there is no error, it's inefficient. If there are errors now, it's even more inefficient. So we have already seen this. So again, just like earlier, I want to put more frames on the line without waiting for this one acknowledgement, even in case of error control. And the two other techniques that we do is what is called go back N ARQ, and we'll see the other one is called selective reject ARQ. So the idea is similar to sliding window. So there is a window size, maximum number of unacknowledged frames that can be there. Same as this, frames are numbered sequentially, just like earlier. Okay, you have a sequence number field in the control fields of the frame, the header of the frame. Okay, and you can send this number of W frames without waiting for the others. So on no error up to this is same as sliding window. Okay, so I have sent, let's say 0, 1, 2, 3, 4, 5, 6, 7, 0, 1. Okay, and let's say all of them go through, 4 does not go through. Can happen. Okay. Okay, I cannot send this many unacknowledged. Okay, so let's just forget about this. Okay, I have sent 0, 1, 2, 3, 4, 5, 6, just suppose. Okay, for my window size of 7. So this goes through, 4 does not go back. So when the receiver gets 5, it knows 4 should come, but it has not come. So receiver detects an error. Either 4 has come, but the frame check sequences did not match, so the damaged frame, or 4 has not come, either of these cases. Okay, it will send a NAC reject for that frame. So it will send a NAC or reject 4, saying this is what I expect next. I've got everything up to 1, 2, 3, but somehow I've not got 4. Okay, and it will discard all future frames received. Is the why it is called go back in. It won't store 5, store 6. Okay, so send not 4, drop 5, 6. So until actually 6 will not be received even. So I'm slightly wrong in drawing this thing. As long as it doesn't get 4, okay, so there's no drop also. Okay, 5, 6 will not be accepted. It is not that it stores and then drops or something. So it's very simple on the receiver side. Receiver says, I expect 4. Until I get 4, I'm not going to do anything. So even if all these other things have come, I'm going to keep on. I got 5, I discard. I got 6, I got discard. 7, I will discard. And sender, when it receives the NAC, that means when it got the NAC 4, it knows only that up to 3 has gone. It's the next expecting 4. But then it also knows that if it has already sent 5 and 6, those also will be rejected by the receiver. So it has to send the frame in error, which is 4, plus all succeeding frames 5 and 6. So you kind of go back something and then retransmit everything from there, not just the frame in error. So sounds really bad, right? Why should the receiver not keep 5, 6 out there? We'll see. Is it clear? What is go back in? Yes, no?
Yes,
okay.
yes, sir.
So this is the one that I will do. The maximum window size with k bit is again 2 to the power k minus 1. So what if not? Okay. So say I have k equal to 3. My maximum window size should have been 7. Let me take 8. Okay. So sender sends frame 0, receives an ACK RR1. So it knows 0 is missing. Okay. Then sender sends frame 1, 2, 3, 4, 5, 6, 7, 0. Next 8 frames. Gets another ACK RR1. Okay. It's got an ambiguity. Did all the 8 frames get through successfully? Or all of the 8 frames were lost or damaged? Which 0 is this ACK saying this? Okay. So ACK, I know that there's an ACK error, I have this NAC reject out there. Okay. But then basically I'm saying that if I get a NAC 0, okay, this 0 that I'm expecting most, okay, Which 0? It is that this 0 itself was not received. Okay, and therefore I have to send all of them, or everything was received and I'm getting the next one. So the k-bit sequence number can give me at most 2 to the power k. I will modify this slightly. Okay, to put it in terms of NAC reject and so on. But you get the idea, and then you can go back to sliding window and do that. And the next one is just what it says. Okay, just what you get from go back here. The common sense thing said if 4 is dropped, 5, 6 is received. Okay, why not just ask for 4? So in this case, the only frames retransmitted are those that receive a NAC or which timeout. So in the earlier case, only 4 will be retransmitted. Which seems like a common sense thing to do, right? And then 5 and 6 will be acknowledged similarly. After 4 is received, 5 and 6 will. So the sender will get a NAC for 4. It will only send 4 and wait for an acknowledgement. If the receiver has received 5, 6, it will send an ACK 7. So sender knows, oh, now 4, 5, 6, all of them has gone through. But it does not resend 5 and 6. Unless it times out for them again and so on. Just the normal thing. Because this ACK, NAC, whatever I'm sending, those also can get lost. But I send only frames that are explicitly told to be an error. Otherwise, my normal operation follows. I send a frame, wait for an ACK, I time out, I send it again normally. But I don't resend everything in error if I know of an error. So in this case, if I get an ACK 4, I will only send 4, assuming that 5 and 6, if I have sent earlier, will go properly. If I time out later on and so on, or an ACK 5 comes again, then I will send 5. All right. So seems to be more efficient, but then there are problems on the basically I've shifted the transmission load to more complexity on the receiver side. Okay. The receiver side requires more buffer space. We'll see buffer space is an important performance metric. Okay. Later on we'll see. As the receiver must keep enough buffer space to save frames received successfully after the framing. Okay, so 1, 2, 3 has got. Now 5, 6 has come. Now until 4 has come, it cannot merge them together and give it to the higher layer. If there is a merging has to be done. Okay, so it has to keep them in buffer. It cannot basically say give it off to whoever needs this and then let me look at other frames. It has to keep it. So now anything else, because the senders may send something more because it is acknowledged up to this, anything else that comes will start getting dropped. So that's one thing. And the other thing is, it's always more complicated to insert the lost frame in the sequence when received successfully later. Okay, so typically we'll know in your actual memory, okay, you will not keep a gap. So that's a wastage of memory. So to trade off this, I will actually keep 1, 2, 3, 5, 6, one after the other. But then when I have to 4, just think of inserting in the middle in an array. Or to shift 5, 6 somewhere else, then put 4, then combine them together and so on. So it has more complicated logic out there. So it's a trade-off. Nothing, again, in design, nothing is perfect. It's a trade-off between you look at your error loss probability and so on, loss probability and so on, and you decide, should I just have simple logic, go back in, and if something gets lost, everything should be transmitted. If my chance of error is low, this probably may not happen too many times. Or should I say that I will have a larger buffer size, build more complicated logic in the receiver, because transmission is costly. I don't want unnecessary frames to be transmitted. And it comes at a big cost at a lower window size. The maximum window size that you can have is no longer 2 to the power k minus 1. It is 2 to the power k minus 1. Again, I would like you to try first finding a counter example the same way. Okay. So read up from the textbook, find a counter example, both for the sliding window and the selective reject, the go back and ARQ I have kind of given you. I'll modify it slightly, wait for my slides. But then, if you cannot do it, let me know. At the beginning of one class, just send me a mail before and at the beginning of one class, I will do. But it's only when you do it yourself, you'll understand what is happening, the dynamics of what is happening. Is it clear? Yes, no?
Yes, sir.
Yes, sir.
Yeah. Okay. So let's summarize. What have we done in this set of slides? Our goal was to make two machines communicate reliably directly with the link. Okay. So what will we do? We'll take the bit stream, whatever. So this is like the file that you are sending and so on. I will break it into frames. Okay. So this is my frame 0, frame 1. I put a sequence number on each of these frames, type of ARQ I'm using accordingly and so on. Okay. For each frame, I'll put a control field, preamble, postambule, and I will send them on their way. Okay. I know how to do it. Okay. And I know that I want to do synchronous transmission mostly because I want this size to be much larger in proportion to this size and this size. Okay. So I need the synchronization. We saw why synchronization needed. Now to synchronize, I need the clock. Therefore, I will do some sort of encoding. So I will have transitions in the data. Even if my original data does not give me transitions, okay, I may have a file which is all zeros, all ones, and so on. I will introduce transitions by encoding. That's what the encode. So I know how to encode. Now it goes to the other side. The receiver looks at the, just waiting for the preamble. It sees this pattern. It says, oh, what is coming else is a frame until I see the postambule pattern. Okay. There are other ways to detect also sometimes. If you have very fixed size frames, then you can see only this many bits and so on. Okay. Now it removes the preamble because that's nothing to do with data. It's just the start of the frame. Control fields does the error detection. Okay. And then the error detection. If it did not detect an error, it just gives, we'll see, to the next higher software that will process it. We'll see, for example, for Ethernet, it will be IP and so on. Okay. If there is an error detected, it drops it. And then there is the flow control and error control techniques that are happening that both sides have agreed on, that guide, that eventually the correct packet will come. Note that there is a non-zero probability that even eventually nothing will come, because there's a non-zero probability that every time you send the data gets corrupted. But usually that does not happen. So in real networks, what happens is that you try for some time, 15 times, 16 times or something, then you give up, saying something is wrong. For example, your link is broken. Then nothing, it will not ever go through. So you don't try infinitely. But for the purpose of the theory, eventually you will get it. But practically, there's a non-zero probability that you may not get it ever. And the system will give up after some number of tries, that is pre-configured. But that's okay. Usually that does not happen. And if it happens, like if there's an error curve, then administrator has to do something to see. So do you kind of believe that this is, you kind of believe me that you can make two machines communicate reliably, connect them with a wire and so on? I'm not saying actually asking you to connect, but if I ask you to design the protocol stack and so on, what all steps you have to do? The encoding and everything below will be hardware and so on. Okay, I'm not asking you to design any of this. Just give me 1 second. Okay? Just 1 second. Yeah, sorry. Yes or no? Okay, start studying. Okay, read some more. And then if you have any questions, then you can ask me. We're going a little slow. Okay. It's 11:52. Let's do it for 5 minutes anyway. We'll just start it and then we'll. So far we have done two devices communicate with a single link. Okay. But then creating a separate physical link between each transmitter receiver pair is infeasible. Okay. We don't want to do that, except maybe at the end some specific cases, okay, where there is there is your computers, as I said, your laptop, desktops are not the only thing that requires networking. So if a device connected with another device, you may want to create only one link between those devices. Okay. But then in many cases, a single receiver pair does not utilize the whole bandwidth. So you connected them even with a UTP cable. The bandwidth is quite large compared to I can send like 100 Mbps, 1 Gbps and so on, 1 gigabits per second and so on. But then how many transmission? Your full HD TV probably requires a few megabits per second. 2, 3, 4, 5, 6 megabits per second. Okay. So one single transmitter receiver pair may not utilize the whole bandwidth. Okay. And you don't want to draw separate wires between everybody also to kind of reduce the cost. So now just try to visualize. I have one medium. Think of a wire on, okay? But I have at the two ends, I need to connect more than one sender communicating more than one. All of their data will go through that same medium. Okay? So how can I do that? First of all, how do I connect? Okay, physically. And then how can I do this thing? So this is what we will deal with in the next thing. And broadly, let me just start off here and end here with two approaches. So multiplexing will do this. It will say, let me kind of slice the channel in some dimension. Let's say time dimension. I say, okay, first 1 second, this sender receiver pair will use it. Next 1 second, this sender receiver pair will use it. Next 1 second, this sender receiver. So I will somehow ensure, don't worry how, that each at any point of time only one sender receiver pair is. So that is, I can slice in time. I can also slice in frequency. I can say basically, oh, I have this 100 megahertz range. Okay, 0 to 10 megahertz will be used only for this two. 10 to 20 only for this sender receiver pair. So I kind of separate out the channels a priori, saying you use this, you use that, and so on. I can separate out in time. I can separate out in frequency. For optical fibers, we'll see I can separate out in wavelengths. I can send different lights of different wavelengths together. So at any, there is no contention for that resource that I'm using. So that is what is called multiplexing. We'll study it tomorrow. And the other thing is what is called, okay, let's not go there, contention, which says, because if I slice it and I give you your 1 second of time, if you don't use the 1 second, the time is wasted. Or if I give you 10 megahertz of signal, if you don't use it, that 10 megahertz is wasted, which somebody could have used. Maybe I have 2 seconds of things to send. You have nothing at this time. I could have used that extra 1 second. So multiplexing is very fixed, static things. We'll see slight changes, not exactly static. As opposed to that, contention-based protocols basically say that when you need it, look for the channel. If it is free, they can kind of compete for the channel. If it is free, send. If it is not, do something. Okay, or even if it is free, do something. But the idea is that a priori I don't reserve anything for anything. Not frequency, not time, not wavelength, nothing. But I say channel is there. When you need it, you compete for it. See what others are doing. If it is free, you do this. If it is busy, you do this. You come back later and do something. We'll see there are different schemes, but that's the idea. But there's no fixed a priori allocation saying this is how you do things, basically. Okay. So this is where we end today. We have gone a little bit slower than what I wanted to today, but that's okay. So tomorrow we need to kind of go a little faster, and we'll directly start with multiplexing techniques tomorrow. All right. So if there are any questions, I will hang around for some time. Yes, go ahead.
Sir, I have some doubts related to the assignment, lab assignment.
Lab assignment. Acha, theek hai. One sec, just one sec.
Yes,
so the class is dismissed. Just give me a second. The class is dismissed. So if you want to leave, you can leave. If you have questions regarding theory or lab or anything, just hang around. Okay. Okay. Now you can ask.
So will there be new lines inside the paragraph, which like in the test case?
I've got a lot of questions on these things. So what is your problem if there are new lines?
So new lines
First
like
first of all, I have sent a mail. Okay, I thought that clarified things, that you will have nothing other than alphanumeric characters, spaces, and full stops. So you can interpret that as with the test case I give you will not have any new lines. Okay.
Okay.
But then again, just for discussion, if you have a new line, what is your problem?
Sir, actually, I'm only handling the full stops and the spaces. So, like the new line character is considered as not being one of them. So it is considered as a character. It is considering as my program.
Yes.
Considering it as a character.
See, if you look at the character count of a file, a new line character also have to be stored.
Yeah,
so it is a character count.
Yeah, it is a character count, but like it is being used as a alphanumeric kind of character.
No. It's not used. No way it is used as an alphanumeric character. Alphanumeric has a very specific meaning.
Yeah. But according to my logic, like I'm like excluding these two, so it is being considered as an alphanumeric, and it's increasing my word count.
Word count. I told you that's I saw. Okay, probably I should have been more careful, but the focus is more on the things. A little bit here and there in word count and all. And as told you, as I sent in the mail, the test case will be on alphanumeric, space, and full stop only.
Okay. And sir, in the end of the paragraph, will there be two full stops to like demarcate the end?
No. See, file is just a normal text file.
Okay.
Now see, the end of, so this is something that somebody else asked me also yesterday. Your end of a paragraph, again, we will not do this in a test case. We'll keep it simple. It's the first assignment. But your end of the file may have a full stop and then two spaces, blanks. Okay. So now you need the two full stops to tell the other side. The receiver needs to see the two full stops. Okay.
Yeah.
So the safe thing to do always is to not rely on the file. You read the file, send whatever is in the file as there. Then you send the full stops at the end. Basically.
Yeah, sure.
But again, if you have used that one full stop and then put another full stop only and so on, that's okay. We'll not worry too much about that.
Okay, and we have to count those two full stops in characters, or we have to exclude them?
One full stop, because the file, you are counting the file, okay, character in the file, and it said that the file will not have two full stops one by one. Then that one full stop should be dropped, right? Again, if your character count, word count goes by the first assignment, goes by, I will test basically with, as I said, only files with space, this, and full stop, one full stop at the end, nothing else after that, and so on. Your character count or word count goes up by 1, 2 here and there, we'll not worry about it.
Okay.
Thanks. Then if you have done some, you think that you have done most of the things correct and all, you will probably lose a little bit of marks. And then again, you can argue with your TA. If, as I said, if not satisfied with your TA, you can tell me.
Yeah, sure, sir.
Okay. Okay. Any other questions? Let me stop the recording.